Everyone, today I will talk about elliptic curve with complex multiplication defined over a real number field. This is a paper authored by P. Clark. I will read to you section 1.3. The delta k is belonging to -3, -4 case. When delta k is belonging to -3 or -4, and the E is a delta is equal to f squared delta k cm elliptic curve, then for some certain f bigger than 1, some of the above steps still hold. However, when f is equal to 1, none of the above arguments hold as stated, while some of the changes are routine. In several places, we have to make arguments that are sufficiently more intricate than those of CL22A. That is another paper authored by P. Clark. Let us describe the modifications here. Step 1A. When delta k belongs to -3 or -4, and the L is a prime number, and the f0 bigger than 1, then again, the L power isogeny graph of delta is equal to L to the L power times f0 to the second power times delta k cm elliptic curve is an Li volcano. When f0 is equal to 1, the L power isogeny graph is no longer an L volcano. This in fact is the least of our worries, as the deviation from volcanoes is minor and had already been well understood. The differences involved multiple edges descending from the surface, and in subtleties involving orientations of edges, which necessitate more care in the notion of non-backtracking paths. The structural information we need is found, for instance, in SU12. That is another paper authored by Sutherland. Step 1B. When f0 squared delta k belongs to -3 or -4, there is in fact no canonical action of complex conjugation on the L isogeny graph. To define the action of complex conjugation on isogenies, we need a priori, a chosen R model on the elliptic curve. So here is an important concept here. We need a priori, a chosen R model on the elliptic curve. A chosen R model on the elliptic curve. That is a parameter where the solution of the parameter, a polynomial, and if we set that polynomial to 0, the solution of that polynomial can be viewed as a model of elliptic curve. And if that polynomial the perimeter of that polynomial are defined over R, then it can be viewed as a R model. R model on the elliptic curve. Every real elliptic curve has precisely two non-isomorphic R models. Okay, this is the key result here. Every real elliptic curve, that is the J invariant of the real elliptic curve. The J invariant of the real elliptic curve is defined over real number field, and every real elliptic curve has two non-isomorphic R model. Every real elliptic curve has precisely two non-isomorphic R models, but they are isomorphic over C, that is the complex number, but they are not isomorphic over R. So every real elliptic curve has precisely two non-isomorphic R models. When delta is less than -4, these two R models are quadratic twists of each other. So this is another important result here. When delta is less than -4, these two R models are quadratic twists of each other. So they have the same J invariant, and the J invariant are defined over real number field R, but they are quadratic twists of each other. So they are isomorphic over complex number C, but the R models are different. So there are two non-isomorphic R models, but they have the same C models. Can you understand it now? So over C, they are isomorphic, but over R, it is not isomorphic. So the action of GR on finite subgroup schemes of E over R is independent of the choice of the R model, because they are quadratic twists of each other. So the Galois group GR acting on the subgroup scheme of the E over R is independent of the choice of the R model. However, when delta is belong to -3 or -4, this is no longer the case. So when delta is -3 or -4, this is no longer the case because the automorphism group is bigger than C2, that is a secret group of order 2. It turns out that when F0 squared delta K is -3 or -4, in most cases we can define a non-canonical action of GR on the L isogeny graph that allows us to determine fields of modulo of delta Cn points on x0 of n in terms of real and complex place, as in CL22A paper. But there are two cases in which we need to pass from this isogeny graph to a certain double cover and define an action of GR on that By looking carefully on how surface edges change the R structure of a delta KCM curve, we are able to carry out the analysis as in C022A paper.